Vou esperar aqui. Pronto.
Okay.
Well, good morning again. Today we'll speak about Hilbert schemes that were used by Hussein in the main lecture some lectures ago. So now we are going to speak a bit about what are the ideas behind these schemes and some of them the steps behind its construction. So what is the idea behind the Hilbert scheme? So our goal is to find spaces that can parameterize schemes inside Pn which have the same numerical characters. So we are going to parameterize schemes inside a projective space, but not all the schemes. We are going to parameterize just families of schemes that have well-defined, like, or have the same, are similar in some sense. And we want to give a scheme structure to the space that parameterize these schemes. And this space will be called Hilbert scheme, right? So this is a natural idea because like we have some specific cases like Grassmannian parameterizing linear subspaces, which are similar schemes inside Pn already, or the projective space, which parameterize lines, which is like a specific case of a Grassmannian. And for example, we could even consider like the space that parameterizes conics that Hussein even spoke a bit about in his lecture, which is actually P5. So, okay, so first we have to define what is the Hilbert function. So we have a field algebraically closed. Of course, we could consider K equals C. That will be the main examples we are going to deal with here. And then we could consider projective schemes on Pn over this field. And of course, all projective schemes correspond to homogeneous ideal in S, which is the space of polynomials. And this scheme, for each scheme, and we have an ideal, and then we can define the Hilbert function to be for each natural, Hilbert function to be a function from natural numbers to natural numbers. And this function will give us the dimension of the n homogeneous part of the quotient. So n homogeneous component. So S is S over I is a graded module, and we could get its homogeneous n homogeneous part and compute its dimension over K, and that is the Hilbert function, right? So this function will be the same as if we compute the Euler characteristic of the shifted structural sheaf and sum it for all the Euler characteristic. But we will see in the next slides why this is true. I'm not going to prove this, but we are going to see. I mean, you can see that this has the shifted. I mean, we will see in the next slides why this is true, but we're not going to prove this. Just see the main ideas. And although this function is only defined for natural numbers, we can extend this function to polynomials. That's the main thing. And then we will call these polynomials Hilbert polynomials. So for example, if we have x equals Pn, that means we are considering the ideal 0. And in this case, age f is just the dimension of the homogeneous component of all polynomials. And this is just n plus n, big N plus small n, this binomial number here. And then this is a polynomial, right? We could just compute. But of course, this is just an example, but we can extend this to a proposition. So for n subscheme, we have that there exists a unique polynomial HP such that HP is equal to HF for all t sufficiently large. The important thing is that it's important to notice that it's not true for all natural numbers. We can extend just for t sufficiently large. And we'll see how it's proven. So here we just use the fact that any graded module, S module, has a finite free resolution of this form. So we could, given by modules of this form, so we could solve any S module by direct sums of shifted S modules by some natural numbers Bj. So if we consider M now, our module to be the quotient, we could get a free resolution. And of course, for modules of this form, we have that the n component, n homogeneous component, is just the n minus b homogeneous component of S. And then, of course, we can compute its Hilbert function, which is polynomial for n bigger than b, because for n bigger than b minus n, sorry, I wrote r here, but it's big N. Because, of course, we have to, this number to be positive. And so, of course, this is polynomial for n bigger than b minus n. And as we have direct sum of modules of this form, we get sum of this kind of function, which is polynomial for big N. So if we take a resolution, we will get something like this, and all these EIs have this form here. And then for exact sequences, we have that the dimension of this space is the alternate sum of the dimension of these spaces here. And this shows that this is a polynomial for large N. And then it's also, we see that we get some alternate sum of this kind of module, shifted modules, which are exactly what we have here, right? So that's the reason. I mean, it's not a proof, but that will be the reason the function will be exactly some kind of characteristic, Euler characteristic. So why we are considering these Hilbert functions, Hilbert polynomials? The thing is that these polynomials encode numerical invariants of schemes. So remember that in the beginning we wanted to consider families of schemes which were similar in some sense. So and this sense in our case will be exactly having the same Hilbert polynomial, because these polynomials encode many important invariants of our schemes. So first, the dimension of the scheme is exactly the degree of the polynomial. So also the degree of the scheme is given by the leading term of the polynomial times the factorial. So if you consider this example here of Pn, you see that the degree is exactly n, because we are multiplying n times. So you have the degree will be this big N, and if we look at the leading term, we will get 1 over n factorial. So that's why we are multiplying by n factorial here. And of course, the degree is the number of intersections with a general hyperplane. And the genus, for example, for a smooth curve, the genus is exactly 1 minus the Hilbert polynomial. And this can be seen by recalling that the genus is just the dimension of the first cohomology. If we use the formula for this formula here, of course, for the Hilbert function. So an example, if we consider a plane curve, the Hilbert polynomial will be given by x plus 2 minus x minus d plus 2 over 2. This is why for any hypersurface, the Hilbert polynomial, Hilbert function will be given by this difference. So the component we are considering plus the dimension of the space, and the component minus d plus the dimension of the space. This is just given by using the famous exact sequence we have for hypersurfaces. And then we have that the Hilbert polynomial is given by this. And the degree of this polynomial is 1. So, of course, the dimension of a curve is 1. And the leading coefficient is the degree. We have to multiply by the dimension factorial, but in our case, it's 1. And then we compute the genus and get this famous formula for the genus, which is the standard formula for smooth plane curves, right? So now this property of having the same Hilbert polynomial has a more algebraic interpretation, and then we are going to, which is called flatness. So a flat module over a ring is a module that makes this functor to exact. So we know that if we have a exact sequence of our modules, if we tensor by M, it will be exact on the right, but not necessarily on the left. And if it's exact on the left, then we call this module M to be flat. For all, of course, it has to work for all exact sequences of our modules. And a morphism is called flat if this module, if for any point this localization, the localization of this morphism in the local rings is a flat morphism. That means that this module OXX is a flat module if we consider it as a module over this ring, right? And a family of schemes is called flat if the projection morphism, of course, if we have a family, we can consider the parameter space, and then we can have the projection from the family to the parameter space. And this family is flat if the morphism to the parameter space is a flat morphism. So the idea is that the flatness is related to some kind of continuity. And that's why it encodes this nice property of having similar schemes in its family. So let's see some examples and understand why it's related to continuity. So now we are going to consider some families over this base space, spec, this parameter space, spec of k of t. This is just some affine line, right? But this is good to making some good examples. So first, what is a family over this space is just some schemes xt for t in k, right? Because of what this space is. And then we can consider the ideals of each scheme. And these ideals, so now we're, okay, so before I proceed, just warn you that I'm considering affine families here for make the examples simpler. But of course, in our case, we were considering projective schemes. But I mean, the main ideas will be the same. So we have the ideals of each scheme in the family. And these ideals can be seen as linear subspaces of our polynomial ring. So, and then, of course, if we want to have a notion of continuity here in these schemes, we could consider the notion of continuity for linear subspaces of this space. And so this is a good way to speak about continuity in this case. So just for you to have an idea, I'm not going to really compute limits in this for linear subspaces and everything, but just for you to know that it's simple to make this everything that I'm going to speak about rigorous, right? So first example is to consider this family. So for each t, we have like 2 points in our affine line. So the point minus t and the point plus t. And of course, we get that for each pair of points, if you get t converging to 0, we are going to get closer and closer points. And then in the limit, we are going to have this space, which is a double point in A1 at the origin of A1. And this is some kind of continuous limit because the points are getting closer and closer and closer, and it's natural to consider this double point as the limit of the pairs of points, right? And this family is flat. I mean, you could compute the flatness algebraically, directly, because if we look at the module in any point here, this will be torsion free over k of t and the localization. So we wouldn't have to worry about flatness. And so we can see the example in the picture. So the pair of points here, t minus t1, t1, t2, minus t2, and they are getting closer and closer to 0. And in this picture, we see the family in the actual A2, because of course our B is A1, right? So we could consider this family in A2, and this space is exactly in this pair of lines, and we are projecting horizontally to our space B. So T1, T2, and that's the picture of the projection of the family. So this picture is good to see how we can work with the family as a scheme itself, right? And now we are going to see two examples, one of a flat family and a non-flat family, to see how it works, right? So first we have the family of these hyperbolas of equation xy minus t equals 0. This is a family if we consider, of course, the spec of xy minus t in this xyt, and is a family, of course, over spec of k of t. This is flat, and I mean, you could compute the modules and see that it's flat up. And of course, if we compute but the important thing is that if we see the picture of all these hyperbolas here, they are getting sharper and sharper if we get t close to 0. And when t is 0, we get the equation xy equals 0, which is just this pair of lines. So we have this natural limit of the hyperbolas. Of course, everyone knows like that when we get sharper and sharper hyperbolas, they get closer to a pair of lines. So, I mean, this makes sense, right? This is like a continuous limit. But if we consider this other family, txy minus t, this is not a flat because we will have some torsion when we multiply by t here because we have this quotient. So if we multiply by t in one side of the tensor product, when we pass the t to the other side, which is possible because we are considering rings over this polynomial ring, or consider our modules over this ring, then it's going to be 0. So we will have some torsion and it's not going to be flat. But the thing is that if we consider the picture, this family will be just formed by the same hyperbola xy minus 1 equals 0, right? Because we can take this t away from, if t is not 0, we can divide everything by t and get the same hyperbola for every t. But when t is 0, we get the whole space here, right? And then, of course, this limit does not make sense, right? If the limit was to be something, it would be the same hyperbola, right? And in this case, for t is 0, we will not have even the same dimension, right? The dimension of the other fibers is 1, and the dimension of the limit, which is not a continuous limit, is 2, right? So this is, of course, not continuous in any sense, and it's not flat also. So flatness is some kind of continuity, and that's why flatness has this geometric property, which we are going to see just now. So, so flatness should preserve dimensions, should preserve these characters, similar spaces, and the proposition that is the theorem or proposition that encodes this is that for any flat family over a reduced base and connected and reduced base, so a family is flat if and only if all fibers have the same Hilbert polynomial. So, I mean, it's a equivalence. So having the same Hilbert polynomial is the same thing as being flat over some reduced and connected base. So that's really nice, right? So this is a really nice characterization. We are not, of course, going to prove it because it's like a very sophisticated result, but it's nice to see that we have this equivalence. And now we can define what Hilbert schemes should be. So we have these flat families, and if we have a flat family of closed subschemes, they will have the same Hilbert polynomial P, and this space HPN, right, will be our Hilbert scheme, and we want to define what is the universal property it should satisfy. So, of course, remember that the family is going to be in the product of the parameter space and the projective space. So the universal property is that for any other family X parameterized by S of closed subschemes with the same Hilbert polynomial, we have a unique morphism S to the Hilbert scheme, satisfying the commutativity of the everything, right? So we can satisfy the commutativity of the projection and the inclusion in the product space. And well, this diagram. So the thing is that the Hilbert scheme should be the set of all flat families, right? Not all flat families, I mean, of all closed subschemes with a fixed Hilbert polynomial. So if we have another family, this family should be inside the Hilbert scheme, right? That's the intuition. So that's why we get this unique morphism. And of course, this diagram has to commute. So that's the universal property. And I mean, as we defined it by this universal property, it has to be unique, right? Because these morphisms are unique. So if we have two different Hilbert schemes, we would have morphism alpha and beta going from one to the other and the other to the one. And then by this commutativity, they would be inverses. It's like a standard argument for this kind of property. And another way of defining Hilbert schemes is to look at this functor here from schemes to sets. So, I mean, schemes of the opposite category. So we want to consider morphisms from in the opposite direction. Just like, I mean, this is simple a contravariant functor, okay? So the idea is that we associate n scheme to the set of all subschemes which are flat over S and have the same Hilbert polynomial, right? So, I mean, we are getting all the subschemes with same Hilbert polynomial, which form, of course, will form a flat family because of the equivalence we saw earlier. And the Hilbert scheme will be the scheme representing this functor. So that means that it will be the functor such that for each scheme S, the set of fibers over points of S having the same Hilbert polynomial will be bijective, will be the same set as morphism from S to our Hilbert scheme. To see that this makes some kind of sense, we could consider, look, I put in the wrong order. So to see this makes some kind of sense, we could look to the second paragraph here and note that if we have any closed subscheme, so one closed subscheme Y, this is a family over spec K, right? Because spec K is just a point. So this is a family over spec K. And if we look at the at this equivalence here, we conclude that the closed points of HPN, which is just the morphism from spec K to HPN, correspond to the scheme Y. So each scheme considered as a family over spec K corresponds to a closed point in HPN. So indeed, HPN is we gave a scheme structure to the set of all subschemes of Pn with same Hilbert polynomial, right? And of course, this definition is equivalent to the definition in the next slide, because for each S, we get a morphism, the morphisms from S to HPN. So for each family here, we get a morphism, right? So that's what we saw before. And finally, we want to give the idea of how we construct Hilbert schemes. So they exist, that's the theorem. And the idea is construct the Hilbert schemes inside Grassmannians. So we have the Grassmannian scheme of key-planes of a M linear space like this. And then for its scheme of the flat family, remember that we have an ideal. And for each M, this ideal is a linear subspace of Sm. So we take this big M to be, to be the dimension of this space, and the small m and this Q to be the dimension of this Im. And remember that as we have the same Hilbert polynomial for all schemes, this dimension is just depends on the Hilbert polynomial, because the Hilbert polynomial is, for each M, the codimension of this ideal, remember? And I mean, we have to make a technical argument to prove that because the Hilbert polynomial just encodes this for M sufficiently large, and we have to prove that this sufficiently large number does not depend on each scheme. This can be uniformized for all schemes in the family. This is a technical argument, but it can be done. And then we can associate that every scheme to a point in the Grassmannian. And finally, you need to show that this is actually a subscheme of the Grassmannian. But this is also not difficult. But I mean, the idea is kind of simple. You just get the ideals and put it inside the Grassmannian. And some examples for zero-dimensional subschemes, the Hilbert polynomial will be constant and equal to the degree of the zero-dimensional scheme. So for varieties, these are just the number of points we are considering in our projective space, like what I did here. And the Hilbert scheme of this family, if we, of course, fix a degree, because we are fixing the Hilbert polynomial. And this is the compactification of the symmetric product of dPNs minus the diagonal. Of course, right? Because the symmetric product, I mean, if we consider just sets of points in Pn, of course, this is parameterized by the symmetric product minus the diagonal, because we cannot repeat points. And then we compactify it to consider the other cases for schemes. Here, the Grassmannian, of course, is the Hilbert schemes of K-linear spaces. K-linear spaces all have Hilbert polynomials given by this polynomial. And for hypersurfaces, as we saw in the case of plane curves, the Hilbert polynomial are this. And the Hilbert scheme associated is exactly the projective space PL for this L given by here. You can see the proofs of these facts in the books I will tell you now. So mostly of the things, the results I stated here are in this book, The Geometry of Schemes of Eisenbuther-Harris, and also in the Geometry of Algebraic Curves of, this is a classical book, of Arborello, Kornauba, and Griffiths. Also, this book, these notes of McLagan are nice to see some computational examples, and she makes some computations using Grobner bases and these things. It's a nice reference. And also I put here Hartshorne book, which is like a classical book in algebraic geometry that can be used to consult about schemes and these general facts of algebraic geometry. So thank you very much. That's everything. Do you have any questions? So thank you very much.